Fish-Black. Professor Fish-Black and Professor Scholes, they published a paper in 1973 about put called European closed form solution. So usually we call it Black-Scholes option model. Sometimes people also add Merton, Black-Scholes-Merton model, because Merton's huge contribution in this area. In 1997, Professor Merton and Professor Scholes won the Nobel Prize jointly because of their contribution in option theory. To understand this video, you should know the basic concept. Again, this is a note. Okay, this is the second video of a set of 3. Please watch the first video if you don't know the basic concept related to the call and the put options. And I put the link here. Please watch the first video before you watch this one. This is the second video of a set 3 video related to the option theory. Here's the agenda. In this short video, I'll discuss the following 5 topics related to the Black-Scholes option model or the Black-Scholes-Merton option model. Topic number 1, an easy way to remember the format of the Black-Scholes call option model. Topic number 2, I'm going to present the model, the formulas. Okay, no derivation, just focus on 3 issues or 3 factors. A, natural log function, Ln, for Excel. B, continuous compounding rate. How to calculate a continuous compounding rate? What is the definition of continuous compounding rate? C, cumulative standard normal distribution and its related to Excel function. Topic number 3, Excel implementation and my VBA code. Topic number 4, put call parity and how to derive a put option from a call option. Topic number 5, implied volatility and its estimation. Topic number 1, an easy way to remember the format of the Black-Scholes call option model. Recall that the payoff for a call long position, this is call option buyer. At maturity, his or her payoff will be max ST minus X or 0. So this means only when ST minus X, then the call option buyer will enjoy a payoff. Okay, so step 0, we draw a timeline. So 0, so this is today. Capital T, this is when the option mature, today, times 0. So actually is present value of stock minus present value of exercise price. The present value of stock is simply as 0. So this is today's stock price. So this is discounting factor E negative RT. So this is exercise price. For the next slides, I'm going to explain this one, continuous compounding rate. Step 5, we add an N function. So present value of stock times N and the present value of exercise price times N. Step 6, so we have add the input D1 for the first N function and D2 for the second N function. So actually step 6, this is exactly Black-Scholes call option closed form solution. Topic number 2, explanation of the model. This is a formula to calculate Black-Scholes-Merton call option. So we know this one. So C equals today's stock price times ND1 minus the present value of exercise price times ND2. So D1, D2. Okay, D1, D2 are calculated by this one. Okay. So S0 is stock price today. X is exercise price. R is continuous compounding risk-free rate. Sigma 2 is the variance of the underlying security. And T is maturity. Log is a natural log function. And N is cumulative standard normal distribution. I mark them in red. I'll explain continuous compounding risk-free rate. I'm going to explain natural log function and cumulative standard normal distribution. Here I'll explain three formulas we are going to use, or three concepts. The first one is called the natural log function, so Ln. And the second one is continuous compounding rate. Suppose if we are given the effective rate, how to calculate continuous compounding rate. For the option theory, the input rate is always continuous compound. The last one is called the cumulative standard normal distribution. Okay. To explain, to make it easy, okay, I start from simplest one. So plus and minus. Okay. So let's assume any value. Okay, value. So value is 2. So x equals 10. Y equals x plus 2. So actually this is 12. It's very, very easy. So this is x plus 2. Okay, so this is from x to y. It's a very, very simple concept, right? So y equals 10 plus 2 is 12. Okay. If one reversed, okay, so this is how to get x. X equals y minus 2. Okay. So this is from y to x. Compounding rate for the option theory and the division. Okay. So let's use 2, and so this is equals x times 2 times this value. And again, we still call it from x to y. So this one is from y. So equals y divided by 2. So this is multiplication. And suppose this is 2.5. Make it a little bit different. So 2.5 times 10 is 25. 25 divided by 2.5. Then we go back to 10. So this is I call the second pair. Okay. The third pair base is 10, and we get this value. Okay. Finally, we get our natural log. Okay, natural log. So the last pair is related to our natural log function. Okay. So actually, it's exponential versus natural log. Okay, Ln. Let's just assume any value, for example 3.8. So this is y. So this is y. Okay. So y will be exponential function. So this we cover this one. So let's use show formula. So we apply exponential function. If we want to recover the previous one, then we use natural log. Natural log. Then we got 3.8. So this is natural log exponential versus natural log functions. equation number 2, actually here it shows how to calculate effective rate. For example, APR is 10%, compounding semi-annually. So M is 2. So 10 divided by 2 is 5%. So effective semi-annual rate is 5%. So let's use some numbers to calculate future value based on equation number 1 or equation number 2. Okay. So present value equals 100. Okay. So this is APR is 10%. Compound semi-annually. So M equals 2. And how many years? Suppose it's 5 years. Okay, so 5 years. So if we apply equation number 2, so this is the future value. So future value equals present value times 1 plus, because this is the effective semi-annual rate, is APR divided by 2. So it's 10 divided by 2. Okay. The power is not 5 years, it's 10 years, because it's 5 times 2 is 10 period. So this is 5 times 2. Okay. The future value is $162.89. So this is based on the equation number 2. Based on the equation number 4, we can calculate continuous compounding rate. Okay, so this is RC. So RC will be M times log, natural log 1 plus APR, so 10% divided by M. So this is 9.758% is continuous compounding rate. Okay, so let's apply the formula. Okay, formula equation number 3, we calculate future value by using continuous compounding rate. So this is future value 2. We call the future value 2 is simply equals present value times exponential. Again, it's continuous compounding rate times t. The only unit for t is a year. Okay, so this is t. Then we got exact same result. I think the key is here to calculate continuous compounding rate. So we apply equation number 4. Now we explain continuous, cumulative, standard, normal distribution, and it's related to the Excel function. Okay. So let's look at the density function, standard normal density function. So let's use -3. So this is x value with is -3. We use 0.25 as incremental value, -2.75. And we copy and paste. That's a little bit more. Okay, so up to 3. So this is a density. Okay, so density function. Okay, normal, standard. Okay, so this is equals norm S. S stands for density. Okay, standard, DIST. So we enter x value. So this is really cumulative. Okay, so it's a force, it's density. So let's try this one. Density. We close it. We copy and paste. So let's choose the graph, density graph. Highlight both columns, insert, recommended. So this is our density. Click OK. This is our density for the standard normal. Okay. The standard normal function is the mean is 0, standard deviation is 1. Okay. So next one, so let's calculate cumulative. The cumulative density function is two exact same function equals norm standard dist. Okay. So this is x, comma, we answer 2, true. So this is cumulative. Okay. So let's draw the graph. So we highlight x column, hold the control key, cumulative, insert, recommended. So this is our cumulative. So cumulative, because the standard normal distribution is symmetric, so this is 50% below 0, 50% after 0. So this is 0 is corresponding 0.5. For the Black-Scholes-Merton option model, we use norm, we use cumulative standard normal distribution. Okay, so let's S0. So let's assume it's $40. Exercise price is 42. That means the option is out of the money. Okay. Time to maturity is half a year. So it's 6 months. Continuous compounding rate is 2%. Okay. Finally, the sigma is 20%. So it's 0.2. Then we calculate the D1 and D2. To calculate D1, we can just plug in the formula directly. Okay. Alternatively, we can make it easy. We can call the temp 1, temp 2, and temp 3. Okay. Temp 1 is simply log S0 divided by X. So this is temp 2, this is temp 3. So D1 is temp 1 plus temp 2 divided by temp 3. Okay, so this is equals natural log S0 divided by X. So this is exercise price. So this is our temp 1. So temp 2 equals continuous compounding risk rate plus half times sigma square. Close it, times maturity T. So this is temp 2. The temp 3 will be sigma times square root of T. So we can use the show formula to show the formula. Okay. So actually, for this one is log B2 over B3. We can copy paste. Then we have 3 formula. For temp 2 equals risk-free rate B5 plus half B6 is standard deviation squared times B4. B4 is T. Okay, so D1 will be temp 1 plus temp 2 close divided by temp 3. Again, we can type show formula. So this is C12 plus C13 divided by C14. So this one will be D2 equals, you see here, D2 equals D1 minus, actually this is times 3. So it's D1 minus times 3. Enter. So this is, so we can also show this formula. Okay, show formula. Okay. So this is call option. So call option will be equals today's stock price S0, so S0 times, okay, so this is normal, standard normal, cumulative, normal, S for standard distribution, D1, so this is D1 and 2. So this is first part, minus exercise price, so X times present value, exponential, negative risk-free rate, times maturity day, times cumulative, normal, standard, DIST. Now it's D2, here is D2, so this is D2, then 2. Okay, so the call option price is $1.59. Okay, then we can copy this formula here. Okay, so this is our formula. Okay, if you want to know how to get the VBA, then you can watch one of my videos called the simple VBA. Okay, okay, so let's use the VBA. So this is we are going to use VBA. So this is method 1. So this is call. Method 2, we use VBA. I joined a VBA called Black-Scholes call. There are two functions. One is call, another help. Always use help first. Okay, help, left, right. Okay, so actually its usage is BS call, S0, exercise, maturity, risk-free, and standard deviation. Okay, so this is equal Black-Scholes call. So this is S0, comma, exercise price, comma, maturity, comma, risk-free rate, comma, and volatility. Then we close it. Then we have exact same result. Again, I'm going to show the formula here. Show formula. Here I discuss implied volatility. I use the same example. Today's stock price is 40, exercise price is 42, maturity is half year, continuous compounding risk-free rate is 2%, so this is given. Okay, volatility is 20%, so this is given. Then we can apply the formula. Okay, show. Okay, so Black-Scholes call help with no input. Okay. Then we use Black-Scholes call according to instruction S0, comma, exercise price, comma, maturity, risk-free, and volatility. We got $1.59. Again, we show formula. Assume we observed the call is higher than $1. So observed call, suppose is $2. is $2 instead of $1.59. Okay, so then what is implied volatility by this observed $2? Okay, without calculation, we should know the volatility should be higher than 20%. The reason is when we increase volatility, price of the call option will increase. Okay, for this case, we can use solver. Okay, solver will be, we click data, we click solve our call premium. So this is 2, exactly 2, by changing our volatility. I repeat, okay. So our object function is our call premium, the formula. Okay, we set this one. We want, so this is maximum, minimum, and value of $2. So this is observed $2 by changing our volatility. Then we click solve. Just click OK. You see this one is higher than 20%, and this is exactly, almost exactly $2. Topic number 4 is about the put-call parity. Its relationship between a put call option and a call option on the same stock with the same maturity and exercise price. Let's look at the future value of the following two portfolios. Portfolio number 1, we have cash. Its future value is X, equivalent to exercise price plus a call options. In the future, if the stock price is higher than exercise price, we exercise our option to own the stock. If the stock is less than exercise price, we let the call option expires. So our terminal values will be max, ST, or X. Which one is higher? Portfolio number 2, we own 1 share and a put options. When the stock price is higher than X, we let the option expire. What's this? If stock price is less than exercise, we sell our stock at X dollars. So our terminal values is max, ST, or X. Because our future value are the same for the two portfolios, their present value should be same as well. Then we have the put call parity. The call premium plus present value of the exercise price equals the put premium plus the value of the stock today.
Shutterstock Music.
Equation number 2, actually here is show how to calculate effective rate. For example, APR is 10%, compounding semi-annually. So M is 2. So 10 divided by 2 is 5%. So effective semi-annual rate is 5%. So let's use some numbers to calculate future value based on equation number 1 or equation number 2. Okay. So present value equals 100. Okay. So this is APR is 10%. Compound semi-annually. So M equals 2. And how many years? Suppose it's 5 years. Okay, so 5 years. So if we apply equation number 2, so this is the future value. So future value equals present value times 1 plus, because this is the effective semi-annual rate, is APR divided by 2. So it's 10 divided by 2. Okay. The power is not 5 years, it's 10 years because it's 5 times 2 is 10 period. So this is 5 times 2. Okay. The future value is $162.89. So this is based on the equation number 2. Based on the equation number 4, we can calculate continuous compounding rate. Okay, so this is RC. So RC will be M times natural log 1 plus APR, so 10% divided by M. Okay. So this is 9.758% is continuous compounding rate. Okay. So let's apply the formula. Okay, formula equation number 3, we calculate the future value by using continuous compounding rate. So this is future value 2. We call the future value 2 is simply equals present value times exponential. Again, it's continuous compounding rate times t. The only unit for t is a year. Okay, so this is t. Then we got exact same result. I think the key is here to calculate continuous compounding rate. So we apply equation number 4.